Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 26, 2026, about 5 days ago. It introduces a generalized server-side anti-cheat system that achieves nearly 91% recall while maintaining a false positive rate of just 4%. The paper is titled XGuardian, Towards Explainable and Generalized AI Anti-Cheat on FPS Games. And as we'll see later, the system isn't just accurate. It processes match replays thousands of times faster than previous methods. Table 1 lays out a comparison between XGuardian and existing solutions, divided into client-side and server-side approaches. The upper rows highlight that prior methods often suffer from limited generalizability or rely on SSL datasets, meaning simulated, small-scale, and low-complexity data. Crucially, notice the interpretability column, where every previous method fails to offer any explanation for its bans. In contrast, the bottom row shows that XGuardian is the only system to achieve full interpretability, while simultaneously delivering high performance on real-world data without the hardware constraints that limit other tools. So Figure 2 illustrates the core data transformation that makes this possible. The top diagram, Panel A, identifies the raw inputs, the player's pitch and yaw angles in the 3D game world, while the grayed out roll axis is ignored since it doesn't affect aiming. In the bottom left, Panel B shows how the system tracks the change in these angles from time t0 to t1. Finally, Panel C on the right demonstrates how this 3D movement is mapped onto a 2D monitor screen plane, allowing the model to calculate critical features like velocity, acceleration, and angular changes. So, with those features defined, Figure 1 outlines the complete operational workflow. On the top left, the process starts with data collection, ingesting standard replay files directly from the game engine to avoid client-side tampering. The top right shows the pre-processing stage, which parses this raw data to filter for elimination events and calculate the specific trajectory metrics we just saw. Finally, the bottom section reveals the dual module architecture. The inspector first classifies the player as a cheater or normal, and then the explainer provides the interpretability layer to justify that verdict. Figure 5 details the internal architecture. On the left, Panel A breaks down the inspector module, which processes data using a sliding window. Each segment feeds into a hybrid network, combining gated recurrent units and convolutional neural networks to capture both temporal sequences and local aim patterns. A random forest classifier then aggregates these signals to render a final verdict. On the right, Panel B illustrates the explainer, which applies Shapley additive explanations to identify suspicious features. The bottom right highlights a novel temporal squeezing mechanism, which condenses overlapping window data into a single, clear visualization for human review. Alright, while the previous figure detailed the architecture, Table 3 now quantifies the system's actual performance using cross-validation. The rows on the left list different permutations of dataset splits, labeled A, B, and C, used for training and testing to ensure fairness. Looking at the results, the system delivers stable metrics, achieving a mean precision of about 94% and an F1 score over 90%. The summary statistics at the bottom highlight extremely low variance, which confirms that the model generalizes well and isn't dependent on a lucky data split. So, having established stability, Table 8 broadens the scope to test generalizability across different games. The columns compare 3 distinct environments: the legacy CSGO data, a mobile battle royale title called Farlight 84, and the primary CS2 dataset. Notice the middle column, where the system handles Farlight 84 on Unreal Engine 4. Even with the lower data precision of mobile replays, the F1 score holds at about 0.83, proving the model isn't just overfitting to the source engine. Well, moving from statistics to visual proof, Figure 10 presents a frame-by-frame breakdown of a detected aim assist incident. The panels track a sequence of game ticks, proceeding from top left to bottom right. For each moment, the system plots the crosshair trajectory at the bottom and identifies the specific metric driving the decision, such as angular change. Crucially, the vertical bars on the right of each frame visualize the Shapley value, which indicates exactly how strongly that specific instant contributed to the cheating verdict. Wrapping up, 2 takeaways stand out. XGuardian proves that using universal inputs like pitch and yaw allows a single system to protect multiple games efficiently. Furthermore, by making AI decisions explainable, it bridges the gap between automated detection and human verification, ensuring fairness in a massive industry. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.